my last lecture, I spoke about the one-dimensional potential barrier. Of course, earlier on we had discussed the one-dimensional square well potential. Now, in the potential barrier problem, towards the end, we realized that the probability of tunneling went down exponentially if the value V0, the value of the potential, the magnitude of the potential, was much larger than the energy of the particle which is trapped on one side of the barrier. The question asked is, what is the penetration across the barrier? And this would exponentially come down if the energy of the particle is significantly smaller than V naught. In other words, as the height of the barrier increases, the probability of tunneling, the probability of leakage across the barrier goes down and goes down exponentially. So, we will remember this and do yet another example of stationary states, a one-dimensional problem, where this time we will discuss a particle in a box. It is a much simpler example than all that we considered earlier, in the following sense, that we imagine this particle of mass m to be inside a box. The walls of the box are impenetrable. So, basically you have infinite barriers for the walls of the box, but the operative word is this: within the box the particle is free to move anywhere. It has positive energy E. The total Hamiltonian is p squared by 2m, where p is the linear momentum of the particle, but then there is no barrier penetration. The walls of the box behave like infinitely high barriers, and therefore, in the region outside the box you will not be able to see the particle. And therefore, in the case of the particle in the box, suppose I have these infinite barriers at x equals 0 and x equals L. The particle is confined between these two regions, these two barriers, and I call these regions 1, 2 and 3. This is a particle of mass m inside a box. Psi 1 is 0, psi 3 is 0. Inside here there is no potential. The particle has energy E, it is a free particle, and therefore in region 2 I have an equation minus h cross squared by 2m d2 psi 2 of x by dx squared is E psi 2 of x. What are the boundary conditions that we can impose? Certainly the wave function must be continuous. So, at x equals 0 and x equals L, we will impose continuity of the wave function. But then, because of this infinite barrier, here there are infinite discontinuities here and there, and therefore, you cannot expect the first derivative of the wave function to be continuous. That will show a finite discontinuity. So, we shall not impose the derivative matching condition at x equals 0 and x equals L. We will merely work with the fact that the wave functions will match psi 1 equals psi 2 at x equals 0 and psi 2 equals psi 3 at x equals L. So, looking at psi 2, we have d2 psi 2 of x by dx squared equals minus 2m E by h cross squared psi 2 of x. And let us call 2m E by h cross squared as alpha squared, which is a positive quantity. And therefore, I have d2 psi 2 of x by dx squared plus alpha squared psi 2 of x equals 0. which leaves me with a plane wave solution inside the box because it is a free particle. I could well write this as psi 2 of x is a sin kx alpha x plus b cos alpha x. Psi 1 is 0 and psi 3 is 0. When I say psi 2, this is the wave function within the box, that is between x equals 0 and x equals L. So now let us match the wave functions at the boundaries. Psi 1 at x equals 0 equals psi 2 at x equals 0. I have selected the box to range between 0 and L, and psi 2 at x equals L equals psi 3 at x equals L. But this quantity is 0 and this quantity is 0. I therefore have the following boundary conditions which will simplify my wave function. So psi 2 of 0 out there, when I match it with psi 1, this simply implies that the cos function out here, b cos alpha x, does not contribute at all, because cos 0 is 1 and therefore b must automatically be 0, and that tells me that psi 2 is a sin alpha x. Of course, a is the normalization. We will have to determine that. At x equals L, I have psi 2 of L equals 0 because psi 3 is 0. That tells me that a sin alpha L equals 0, since a in general is not 0, because then the wave function itself will vanish. I have alpha equals n pi by L, where n can take values. I cannot put 0, because if n were 0, then alpha is 0. Recall that the energy is related to alpha. Alpha squared is 2m e by h cross squared, and then the energy will be 0. So n is equal to 0 is not an allowed solution. On the other hand, n equals 1, 2, 3, also plus minus 1, plus minus 2, plus minus 3 in general. But if n is minus, out here it is simply going to give me the same function, because sine of minus x is minus sine of x. I do not get anything independent. That is just an overall phase that will come out, and therefore this is the solution. Alpha is n pi by L, where n takes values 1, 2, 3, and therefore psi 2 of x is a sin n pi x by L. Have to determine a, the normalization constant. The normalization is done by looking at the entire interval, but from minus infinity to 0, psi is 0, so that does not contribute. Again, from L to plus infinity, the wave function vanishes, so there is no contribution. The only non-zero contribution I need to worry about is integral 0 to L a squared psi star of x psi of x, which is psi sine squared n pi x by L dx. This quantity is normalized to 1. This is in fitting with the probabilistic interpretation, because this is the same as saying that this object is equal to 1. Let us recall that because we are working in the position representation, I have integral psi star of x psi of x dx equals 1, and that should determine a squared for me, because I could of course write this as half 1 minus cos 2 n pi x by L and do the integration. So, that tells me that a squared by 2 integral dx from 0 to L minus integral cos 2 n pi x by L dx. This quantity is 1. That is not going to make a contribution and this gives me just an L. So, a squared times L by 2 is equal to 1, or a is root of 2 by L. I have not chosen minus root of 2 by L because wave functions anyway are arbitrary up to a phase. And therefore, my wave function, I will drop this suffix, the subscript 2 out here, and I will write psi of x is root of 2 by L sine n pi x by L, n is 1, 2, 3 and so on. So, this is the wave function psi of x. I should in fact put psi n of x out there because there are very many states, eigenstates of the Hamiltonian, because this is indeed the solution to the Schrodinger equation. What are the corresponding energy levels? We decided that alpha was n pi by L, and since alpha squared is 2m by h cross squared, it implies that E sub n is n squared pi squared h cross squared by 2m L squared, n taking values 1, 2, 3 and so on. So, these are the eigenfunctions. So, if you put a particle in the box, there are discrete energy levels, call them E sub n, and the expression is E n is n squared pi squared h cross squared by 2m L squared, and the corresponding wave functions are given by root of 2 by L sine n pi x by L. So, that is what we have. Now, given this, we would like to see what the uncertainty product is like, specifically in the ground state of the particle in the box, because we know that for the harmonic oscillator problem, the one-dimensional oscillator problem that we have already handled, the ground state was a minimum energy state, minimum uncertainty state, and delta x was equal to delta p, and the uncertainty product got equalized in the ground state. So, let us see what happens here. So, the aim is to calculate the uncertainty product in any state of the particle in the box. So, we need to compute delta x and delta p. Recall that delta x squared is expectation x squared minus expectation x, the whole squared. Similarly, delta p squared. So, we begin with expectation x. The expectation value of x in any state is integral psi star x psi. So, that gives me a 2 by L sine squared n pi x by L times x dx. Now, before I compute this integral, I would like to argue and find out what would be the value of x. So, this particle is not biased towards any particular point or in any particular direction. It is a free particle moving anywhere within the box and incapable of penetrating outside the box. In that case, on an average, you would expect that x would take the value L by 2, because that is the average of 0 and L. So, I would expect the mean value of x to be L by 2. We can always do this calculation explicitly and see if indeed that is true. This is 2 by L integral x 1 minus cos 2 n pi x by L dx by 2, and therefore, I might as well write this as 1 by L times this. Well, the first term in the integral from 0 to L is just integral x dx, and this is from 0 to L. So, the first term just gives me an L by 2, which is what I thought would happen, but I have another integral which is minus 1 by L integral x cos 2 n pi x by L dx. You can use integration by parts, and that quantity vanishes. It is a trivial integration, and indeed my guess was right that expectation value of x is L by 2. So, on an average the particle has no preferred direction, moves anywhere inside the box like a free particle, not subject to any potential, and therefore the average value of x would be L by 2, because the boundaries were at x is equal to 0 and x equals L. So, let us put that down somewhere. We have E n is n squared pi squared h cross squared by 2 m L squared, n equals 1, 2, 3 and so on, and psi n of x is root of 2 by L sin n pi x by L. Expectation value of x in the state psi sub n is L by 2. So, it seems to be independent of which excited state the particle is in. That is all that we have, but expectation x squared is not so trivial. We can compute the integral, and that is going to be a function of n, and therefore there is going to be a variance which gets a contribution both from the mean value of x and from x squared's expectation value. So, let us compute that. Expectation x squared is of course 2 by L integral x squared sin squared n pi x by L dx. This object is again 1 by L integral 1 minus cos 2 n pi x by L x squared dx. The integral of course goes from 0 to L. Well, the first term gives me an integral x squared dx, which just gives me an L squared by 3 with the 1 by L. Then I have a minus 1 by L integral 0 to L x squared cos 2 n pi x by L dx. This integral again can be worked out explicitly. You can use integration by parts, call this u, call that dv. So, if that is dv cos 2 n pi x by L dx, if that is dv, v is a sign. So, the term uv has x squared sin 2 n pi x by L, and then there is an integral v du which will make a contribution, and you can simplify this. It is a simple integral, and the answer is minus L squared by 2 n squared pi squared being the contribution from here. So, this is what we have for expectation x squared. As you can see, there is an n dependence in the expectation value of x squared, and for large quantum numbers the contribution from this term goes down. This is a point I will comment on a little bit later. So, let us put down that result. This is L squared by 3 minus L squared by 2 n squared pi squared. Then of course, one should be careful with dimensions. If you are talking of expectation x, it has to be the first power of L. If it is expectation x squared, the dimension comes from L squared, and therefore delta x the whole squared is L squared by 3 minus L squared by 2 n squared pi squared minus L squared by 4 from expectation x the whole squared, which is L squared by 12 minus L squared by 2 n squared pi squared. This is what I have, and therefore the variance, so I can well write this as L squared by 12 times 1 minus 6 by n squared pi squared. That is the variance, and therefore, delta x is L by root 12 1 minus 6 by n squared pi squared to the power of half. So, that is what I have for delta x. So, now let us find the variance in P. So, delta P the whole squared, that is the square of the variance, as you know, is expectation P squared minus expectation P the whole squared. So, what is expectation P? This object, my wave function is root of 2 by L sin n pi x by L. So, I pull out a 2 by L integral sin n pi x by L. I write P in the position representation as minus I h cross d by dx. So, that is a psi star psi. Of course, the integral limits go from 0 to L. The wave function is a real wave function, and therefore, psi star is the same as psi, and we are working in the position representation. So, this object, apart from a minus I h cross which I can pull outside, is simply sin n pi x by L, n pi by L cos n pi x by L dx. And this integration, if I do it, I will get 0. In fact, I can come up with a very reasonable argument as to why this should be 0, because the particle will, caught in a square well, will move as much to the left as to the right, and so on an average I would expect the net momentum to be 0. On the other hand, there is a contribution from expectation P squared to the square of the variance. So, once again I can find this as before. I have psi star psi, but now it is a minus h cross squared d2 by dx squared sin n pi x by L, because I have substituted for P squared. I could do this integration. On the other hand, I can come up with a nice argument as to what it should be. Look at expectation P squared. Now, E sub n is n squared pi squared h cross squared by 2m L squared, and therefore, P squared you know that E is P squared by 2m, and therefore, P squared is n squared pi squared h cross squared by L squared. In fact, it is P n. And this is what makes a contribution to delta P squared, not from here, but from expectation P squared. Of course, I can explicitly work out this integral, and if I did that, I would get this answer. So, let us write that down here, and expectation P squared is n squared pi squared h cross squared by L squared. I can now compute delta x. Delta x is simply expectation P squared, delta P, that is simply expectation P squared, and that is n squared pi squared. Delta P the whole squared is n squared pi squared h cross squared by L squared, and therefore, delta P is n pi h cross by L. I now compute the uncertainty product delta x delta p in the state psi n. I have got delta x there, so it is easier to do delta x squared delta p squared. So, delta x squared is out here, it is L squared by 12 times 1 minus 6 by n squared pi squared times delta p squared, which is n squared pi squared h cross squared by L squared. And that gives me quantities. The first one depends on n squared, and in the second one you will see that n squared cancels out. The first one, the L squared cancels out, and I get an n squared pi squared h cross squared by 12 minus h cross squared by 2. We can therefore now find the value of the uncertainty product, say in the ground state of the particle in the box, setting n equals 1. So, let us do that. Delta x delta p in the ground state for n equals 1. So, delta x squared delta p squared is pi squared h cross squared by 12 minus h cross squared by 2. We can now put in the value of pi, and you can see that the uncertainty product delta x delta p is greater than the minimum value, because it is roughly 0.57 h cross. This is therefore not a minimum uncertainty state. It is obvious that the higher energy states are even worse, and there is no minimum uncertainty state in the case of the particle in a box. The ground state is not a minimum uncertainty state, and the other states are even worse. In the sense, delta x delta p is larger than its value for the ground state. You can substitute n is equal to 2, 3, 4 and so on out here. There is an interesting observation that one can make at this point. How do you go to the classical limit of the problem? In classical mechanics, the energy levels are not discrete, they are not quantized. Now, for this particle in a box, the energy level must be a continuum of numbers, and when do I hit the classical limit? I hit the classical limit, of course, when n becomes very large. H cross has to go to 0 to get to the classical limit. So, the classical limit is reached for n going to infinity and h cross going to 0. At that stage, I would really retrieve the classical features, because the difference between n plus 1 the whole squared and n squared goes down for large n compared to values where n is small, and therefore, as you consider larger and larger values of n, it is clear that the energy levels get closer and closer to each other. This is simply a constant. The energy levels get closer and closer to each other if you look at E sub n. And you no longer see the separation very clearly. In other words, you hit the continuum, or you have hit something that looks like a continuous stretch of states, or you have hit the classical limit. So, now let us look at the classical limit of this problem. What exactly happens in classical physics? In classical physics, I can talk of the probability distribution of x and so on. So, let us look at the probability distribution. The probability distribution of x would be uniform in classical physics for this problem, because the particle can be anywhere with equal probability, and therefore, p of x, let me call it p classical of x, this would be 1 by L. It is anybody's guess, because you know that the total probability has to be 1. That of course implies that p classical is 1 by L. That gives me an integral dx which is an L, and things neatly cancel out. So if this is P classical, I can find out the value of the mean value of x, the mean value of x squared and so on in classical physics. So the mean value of x, let me call that x classical, the mean value x classical. This object is simply integral x P classical dx from 0 to L, and that is 1 by L, L squared by 2, which is L by 2. So both in classical physics and in quantum physics, I would expect this to be the average value of the position, L by 2. Not surprisingly, therefore, even in the classical limit, the quantum value is simply the same as the classical value, it is L by 2. Now look at expectation x squared, classical. I use this notation to show the average value in classical physics. Now that is 0 to L, x squared P classical of x dx, that is 1 by L, x cubed by 3 between 0 and L, so that is L cubed by 3 which is L squared by 3. This is what I have for expectation x squared classical, that is L squared by 3. Now look at the expectation value of x squared here. In the quantum mechanical analog, where the particle was a quantum particle in the box, you have an L squared by 3 minus L squared by 2 n squared pi squared. Now in the limit of large quantum numbers, for n going to infinity, you find that expectation x squared quantum goes to the classical limit which is given here, which is L squared by 3. So that's one thing that we've checked out. Now look at expectation value of P. I would use the same argument that I used in the quantum case for expectation value of P. The particle can go anywhere to the right and to the left with equal probability, and therefore on an average I would expect its momentum to be 0. The velocities to the right and to the left would be occurring with equal probabilities, and therefore I would expect expectation value of P to be 0. As to delta P itself, in the quantum case, I had delta P to be essentially given by expectation P squared, because expectation P was 0, and expectation P squared is delta P the whole squared, which is n squared pi squared h cross squared by L squared. And what should it be? I know that this should simply be 2m E classical, because P squared by 2m is indeed E classical in the classical case, and therefore expectation value of P squared square root gives me delta P, which should be square root of 2m E classical. So this is the way one goes from the quantum case to the classical limit. There is one very interesting aspect, so much for the uncertainty. There is one very interesting aspect to this problem, and that comes by looking at the momentum space wave function and the probability density in momentum space. The momentum space wave function is clearly obtained by doing the Fourier transform of the position space wave function. So in the Dirac notation, for instance, I would denote the momentum space wave function psi tilde of P as this inner product bra P with ket psi. This can well be written as P x x psi. I am talking about quantized energy levels, and therefore I might as well write psi n dx. Really this should go from minus infinity to infinity in general, and I have introduced a complete set of states. The right hand side is the identity operator. This object here is simply psi n of x. It is the nth eigenstate in the position representation. but I know that psi tilde of p is related to psi n of x through the Fourier transform. So basically this object here is e to the I p x by h cross, but I would also do a root of 2 pi h cross. That is when I go from the position space to the momentum space. I have psi tilde of p is equal to 1 by root of 2 pi h cross integral over the allowed values of x e to the I p x by h cross psi of x. I should really write psi n tilde of p if I have psi n of x dx. The root 2 pi here is of course a convention, because I could have put a 1 by root 2 pi h cross here, and when I do the inverse Fourier transform I will put a 1 by root of 2 pi h cross when I go from psi tilde of p to psi of x. I could instead not have the 1 by root 2 pi at all in one case. I could have made this 2 pi h cross and nothing out there, just 1 out there when I go from the momentum space to the position space. Equally, I could have kept 1 here as a coefficient, removed this, and I could have transferred 2 pi to the other side. And so when I come from the momentum space to the position space doing an inverse Fourier transform, I could introduce a coefficient 1 by 2 pi. So those are conventions, and I use this convention, and this is what I have. So this is the momentum space wave function, except that now I need to put in psi n of x between x is 0 and x is L, and therefore psi n tilde of p is really going to be integral 0 to L e to the I p x by h cross root of 2 by L 1 by root of 2 pi h cross sine n pi x by L dx. So this is the integral that one has to do in order to find psi n tilde of p, the momentum space wave function. One can do this integral and find modulus of psi n tilde of p the whole squared, and that is going to be the momentum space probability density. So if you plot that distribution versus p, you see something pretty interesting. Modulus of psi n tilde of p the whole squared can be computed, and if you plot modulus of psi n tilde of p versus p, defining p sub n as n pi by L, the plot of modulus of psi n tilde of p the whole squared versus p takes a maximum, is symmetric first of all, it takes a maximum at plus Pn and minus Pn, at these two values plus Pn and minus Pn. Mod psi n tilde of p the whole squared picks up maxima, and interestingly the minimum value is at p equals 0. This is a point to note because expectation value of p was 0, while the mean value of p is 0. P 0 is the lowest probability point, because you find that the probability distribution really peaks up at p is plus Pn and minus Pn. So the average value is really the lowest probability value for this distribution, and that is a very important and interesting point to remember in the context of the case of the particle in the box. So we have seen 3 situations: the particle in the box, the square well potential, and the infinite potential barrier. These are all examples of stationary states, and several interesting quantum properties emerged in the process. There was tunneling, leakage across the well, into the classically forbidden region, tunneling across the barrier. The manner in which the quantum limit went to the classical limit itself comes for large quantum numbers where n goes to infinity and h cross goes to 0. We have seen the free particle solution. Psi is a plane wave solution, e to the ipx by h cross or e to the minus ipx by h cross. We have seen the harmonic oscillator, the one-dimensional oscillator, where we had the ladder operators B and B dagger, and we had discrete energy levels and essentially the Hermite polynomials as the energy eigenstates. Now to a last and very interesting problem in this category, and that is the case of a charged particle in a homogeneous magnetic field. You will find that this spectrum in essence has a part which behaves like the linear harmonic oscillator spectrum and another part which behaves like the free particle. So there is a combination of both the harmonic oscillator and the free particle in the case of the problem of the charged particle of mass m moving in a homogeneous magnetic field. So let me just set up the foundation for that, and then in tomorrow's lecture I can look at the details of this problem. So we now discuss the problem of a charged particle in a homogeneous magnetic field. Particle of charge, particle of mass m and charge E subject to a homogeneous magnetic field. Subject to a magnetic field where we will approximate, we will simplify it to a homogeneous magnetic field a little later. The Hamiltonian for a free particle is p squared by 2m. As you know, p is the linear momentum of the particle. Now in the presence of a magnetic field, you do a minimal coupling and p itself is replaced by p minus Ea by c, where A is the vector potential. The magnetic field itself is related to A by B equals del cross A. So let me call this as capital P, not pi, capital P, like that. The Hamiltonian then is p squared by 2m, where p is defined, the vector p is simply the linear momentum of the particle minus Ea by c. This prescription, p goes to p minus Ea by c, leads to something called the minimal coupling, because when you do the square, there are terms which involve p dot A dot p and so on, and that is the coupling between the particle with momentum p and the vector potential A of the field that we are talking about. And this is a minimal coupling. One can think of more non-minimal terms, but that is beside the issue right now. We shall work with the minimal coupling prescription. So this is obviously going to have three components, px squared plus py squared plus pz squared by 2m. Now it is clear that the magnetic field is the physically observable field, is a physically observable quantity, and not so much the vector potential A, in the sense that several A's, in fact an infinite set of vector potentials, could give me the same magnetic field, because if I replace A by A plus gradient of a scalar quantity, I would still get the same B. So I can do what is called a gauge transformation on A. A goes to A plus grad chi. Chi is a function of space time and chi is a scalar. Then B is now del cross A plus grad chi, which is del cross A plus the curl of a gradient, and that is 0. And therefore, there are, in principle, I can choose chi to be anything I wish, any scalar function, and therefore, for an infinite set of vector potentials, I get the same magnetic field B. The Hamiltonian is given in this manner. I would like to make this magnetic field homogeneous, in the sense I would like to choose B to be a constant magnetic field independent of space and time along the z direction. The direction of B is chosen as a reference axis or the z direction. Now, in that case, Az will be 0, because B is equal to, if B is equal to BEZ, Az is 0 and Ax and Ay in general non-zero. It is possible for me, since I have already explained that different A's could lead to the same B, it is possible for me to choose Ax and Ay non-zero for a given B. I could choose Ax to be 0 and Ay to be non-zero for the same B, or Ax to be non-zero and Ay to be 0, get the same B. So, by gauge transformation, that is by changing a given value of A to A plus grad chi and choosing my chi appropriately, I can have an infinite set of vector potentials which will give me the same B. I choose a gauge by fixing a certain value of Ax, Ay and Az. In this case, Az is 0, and depending upon the choice of Ax and Ay, I would say that I have selected a gauge. So, we will work out the problem of the particle in the homogeneous magnetic field, get the eigenspectrum, the energy eigenspectrum and the eigenvalues for specific gauges. That means for specific choice of Ax, Ay and of course Az equal to 0. This is what we will see in the next lecture.